This is Module A7, Objective 10, and in this objective, we're going to look at visceral reflexes. We find that the autonomic nervous system is also organized into a series of interacting levels. At the bottom are the visceral motor neurons in the lower brainstem and spinal cord, and these neurons are involved in cranial and spinal visceral reflexes. Visceral reflexes provide autonomic motor responses that can be modified, facilitated, or even inhibited by higher centers, especially those of the hypothalamus. Complex reflexes coordinated in the medulla include salivation, swallowing, digestive secretions, peristalsis, and urinary function. Peristalsis is the rhythmic muscular contractions found in certain organ systems, such as the digestive system, as food moves from your mouth to your anus. These rhythmic muscular contractions help propel the substance through the digestive tract. And all of these reflexes, complex reflexes, are coordinated or regulated by the hypothalamus. The integration of the somatic nervous systems that we've already covered and the autonomic nervous system are very similar. They have many parallels in terms of the way that these systems are organized as well as how they function. The integration of these two systems occur at the brainstem. This is figure 1612, and it looks at a comparison between the autonomic and somatic functions. You can see that sensory receptors are going to pick up sensations and carry that up towards the brainstem via the afferent division. And the level of the brainstem, we can, through visceral sensory, send that to the hypothalamus where effectors can be activated. Of course, this is compared to the somatic, in which somatic sensory would then carry the information from the brainstem to the thalamus and then to the cerebral cortex, where effectors could be consciously activated. Excuse me, I dropped my pen. All right, in Objective 11, we're going to look at memory creation as well as levels of consciousness. All higher order functions require the cerebral cortex. They involve both conscious and unconscious processing, and they're not part of the programmed wiring, the hard wiring that came with your brain. So these higher order functions can often they can adjust over time. We're going to start out looking at memories, and memories can be classified as fact memories versus skill. Fact memories are little tidbits of information. A stop sign is red, and we all know what a stop sign looks like. These are little fact memories, while skill memories are learned motor behaviors. The textbook uses the example of unscrewing a lid to a jar. This, through repetition, through many years of unscrewing lids, you have built up a skill memory. Memories can be classified as short-term versus long-term. Short-term memories is small bits of information that can be recalled immediately. These are also known as primary memories. If short-term memories are not converted to long-term memories, they're lost. Long-term memories involve memory consolidation. Memory consolidation is the conversion from a short-term to a long-term memory. In terms of long-term memories, we can identify secondary memories and tertiary memories. Secondary memories tend to fade. They require a bit of effort in terms of trying to recall that memory. For instance, often I see students from past semesters. I recognize their face, but I cannot recall their name. This is a secondary memory that has faded over time. Tertiary memories are those memories that tend to stick with us for life. Your name is a tertiary memory. You will remember your name, hopefully, for life. This is figure 1613, memory storage, and it kind of incorporates all the different types of memories. So memories require some type of sensory input. You watch something, you listen to my voice in these lectures, and hopefully it creates a short-term memory. Now, if the short-term memory is reviewed repetitiously, it's going to promote retention, and this is what we want. Retention. If not, it's permanently lost. With short-term memory, our next step would be consolidation. Consolidation is the conversion between short-term memory and long-term memory. And once you convert that information to long-term memory, you have secondary memories and tertiary memories. Secondary memories need to be, at times, repetitiously reviewed. If not, you can get temporary or permanent loss. And tertiary memories are those memories that are with you for life. When we look at memory consolidation, there are three regions of the brain associated with that process. What is consolidation again? It is the conversion of short-term memory to long-term memory. These three regions are the amygdaloid body and hippocampus, the nucleus basalis, we haven't talked about this region, and the cerebral cortex. The amygdaloid body and the hippocampus, you should recognize both of these structures as regions belonging to the limbic system. I'm just going to put limbic here to trigger that memory. And these two regions are essential in memory consolidation. Clinicians have found that when these regions of the brain become damaged, the individual loses the ability to convert short-term memories to long-term memories. The cerebral cortex stores long-term memories. And we find that there are a number of association areas. The occipital and temporal lobes of the cortex, these are special regions that are crucial to the memories of faces and voices and words. We find that a specific neuron, one neuron, may be activated by a certain combination of stimuli, sensory stimuli, associated with a person, a particular individual. And these neurons are referred to as grandmother cells. When you look at the cerebral cortex, there's often a lot of different there's a lot of different regions of the brain that interact. The book uses the example of a cow, and I think I'll continue with that. So the information on the cow is parceled out to many different regions of the brain. Your memories of cows are stored in the visual association area. This is what a cow looks like. And what the letters COW mean. The auditory association area will hold the memories associated with the noise that a cow makes, the moo. We have speech centers that store the information on how to say the word cow. The frontal lobes, for instance, store information on how big cows are and what cows eat, and so on and so forth. So what we see is that there's a tremendous amount of different regions of the brain associated with particular memories. And that any type of damage, if you were to take out the auditory association area that holds the information for the sound that cows make, we find that your memory is incomplete. You might be able to know what a cow looks like. You might be able to identify the letters, but you're not going to have the association areas that deal with the sound. So you have an incomplete memory. When we look at the cellular mechanisms of memory formation, we see that it's both anatomical and physiological changes that take place. And we can identify three major changes. You can have an increase in neurotransmitter release, facilitation, a term we'll define in a minute, at synapses, and formation of additional synaptic connections. Increased neurotransmitter release. What we find is that active synapses will increase the amount of neurotransmitter stored. These synapses will then release more neurotransmitter at each stimulation. And of course, the more neurotransmitter is going to have a greater effect on the postsynaptic neuron. Facilitation. What occurs in facilitation when a particular neural circuit is repeatedly activated, we find that the synaptic terminals begin to continuously release neurotransmitter at a very low rate. Those neurotransmitters will bind to the postsynaptic membrane. They will then cause a graded potential on the postsynaptic membrane, a graded depolarization. This will bring that membrane closer to threshold, and ultimately it's going to make it easier for that particular membrane to reach threshold. So that is what facilitation is. Lastly, we can have the formation of additional synaptic connections. When you have a tremendous amount of communication occurring between two neurons, what you find is that the presynaptic neuron will start sending out other synapses. Okay, the axon tip branches and forms additional synapses on the postsynaptic neuron. This is going to have a greater effect on the transmembrane potential in that postsynaptic neuron. In terms of the basis of memory storage creates anatomical changes at the cellular level. And these facilitate communication along very specific neural circuits. We could talk about a memory engram, where a single circuit corresponds to a single memory. Let me just talk about circuitry. Here we have a circuit. It is a linear array of neurons. So this particular circuit corresponds to a single memory. And these circuits will form as a result of some experience and repetition. So these are the anatomical changes, the linking up of particular neurons to form a circuit. And if that circuit is associated with a single memory, that would be a memory engram. efficiently convert short-term memory to long-term memory, it takes about an hour. And repetition is crucial. I cannot say this enough. You really need to repetition as you're learning the material in this course. Through repetition, you can convert or consolidate those short-term memories into long-term memories. And that is what you need to be successful, especially on a comprehensive final. In terms of the factors of conversion or consolidation, they depend on the intensity or the nature of that original stimulus. We find that strong, repeated, either pleasant or unpleasant events they're likely converted to long-term memories. I doubt anybody here remembers, but I remember hearing that in school when we were taking history that individuals of a particular generation, they all remember where they were this moment that they heard that John F. Kennedy had been assassinated. This was a very unpleasant, shocking event that was quickly converted to long-term memory. Again, most of you remember the Twin Towers and all of the news cast that followed that event. And again, that information was converted to long-term memory because it was something that was very unpleasant, as well as something that through repetition we were exposed to. Certain drugs can stimulate the central nervous system. Caffeine and nicotine are examples. These two substances enhance memory consolidation through facilitation. What is facilitation again? You probably should stop and go back and reread that little section if you have forgotten. And then consolidation as well, the conversion of short-term to long-term memories. Another substance we'll look at are the NMDA receptors. This is the N-methyl D-aspartate. These receptors are linked to consolidation. They are chemically gated calcium channels activated by the neurotransmitter glutamate. I believe your slide says glycine, and glycine is incorrect. I was rereading the text and I found a mistake. It is the neurotransmitter glutamate. And this neurotransmitter will open the calcium channels. Calcium will enter the cell. And we find that blocking the NMDA receptors in the hippocampus prevents long-term memory formation. So it does play a role. I'm going to continue with another video lecture covering states of consciousness, so we'll just kind of stop here and take a breather.